Today we're going to talk about non-removable discontinuities, the vertical asymptote kind. So first we start off with this rational expression, this rational function, and it's a function of x. The numerator is a polynomial in x. The denominator is also a polynomial in x, but I've written it in its factored form. So the leading coefficient a has been factored out, and then I have a bunch of factors of the form x minus c, x minus r2, x minus all the way up to rn. So there are n factors here, n zeros. I'm looking at one of the zeros, c, the very first one. When you plug in c, the f of c, you'll have down here c minus c, which equals 0. And when you multiply the entire denominator by 0, you get 0, so it'll be undefined. Therefore, I'm going to mark off the value c so we don't plug it in. We know we cannot get a value. There's no y value at c. So we're going to approach c from the right-hand side. We're going to choose a number that's to the right of c but kind of close. And then we're going to choose another number that's even closer to c. So we're going to start out from the right and go towards the left, getting progressively closer to c. And we find that the y values just increase, continue to increase, like this. Then we will say that as you approach c from the right-hand side, the y values are approaching an infinite value. They just keep getting larger and larger and larger, approaching infinity. So we use this notation that says the limit as x approaches c from the right-hand side, so that little superscript plus sign means from the right-hand side, of the function f of x, remember the function is f of x, is equal to infinity. Meaning, as I get closer and closer to c from the right, the y values of the function are getting closer and closer to infinity, just increasing without bound. Let's see what happens. Well, what happens if I start approaching c from the right side, but instead of the values getting larger and larger and larger, like that case, what if the values get smaller and smaller and smaller? Well, in that case, it would look like this. As you approach c from the right side, the values get smaller and smaller and smaller. And in that case, we would use this notation. We say the limit as x approaches c from the right-hand side, so the superscript is still a plus, of the function f of x is equal to negative infinity, meaning as x gets closer and closer to c from the right-hand side, from numbers larger than c, y is getting smaller and smaller, going to negative infinity. We don't have to approach c from the right-hand side. We could also approach c from the left side, so we could be coming from numbers smaller than c and getting closer and closer and closer to c by getting larger and larger values of x that are still smaller than c. Now if we do that, and as we get closer and closer to c, from the left-hand side, the values of y get smaller and smaller like this, decreasing without bound, then we use this notation to say that the limit as x approaches c, and instead of a plus sign, now we have a minus sign. So the limit as x approaches c from the left now of the function f of x is equal to negative infinity because the values are decreasing rapidly without bound. From the left again, it could happen that as you get closer and closer to c, the y values are getting larger and larger without bound. And in this case, we use this notation to say the limit as x approaches c from the left side of f of x is equal to infinity, positive infinity in this case because it's increasing without bound. Here's an example. This is a very simple example. The numerator is just the constant 1, and the denominator is the binomial x minus 2, a linear binomial. The 0 of that binomial is the number 2. So if we plug 2 in to this expression, the expression will be undefined because 2 minus 2 is 0, 1 over 0 is undefined. That means 2 is a value that cannot be plugged in to this expression. You have to avoid plugging 2 in, so we'll mark off 2 so we don't plug it in. And then we're just going to go ahead and plug in numbers and approach 2 from the left-hand side. So I'm going to plug in numbers closer and closer to 2, but from the left-hand side. So I'm going to plug in a number like 1.9. And when you plug in 1.9, 1.9 minus 2 is negative 0.1, and 1 over negative 0.1 is negative 10. Then if you plug in a number like 1.99, that number is even closer to 2 than 1.9 was. 1.99 minus 2 is 0.01, negative 0.01. 1 over negative 0.01 is negative 100. And then I'll plug in a number like 1.999. That's even closer to 2. So I plug in 1.999, that's 1.999 minus 2, which is negative 0.001. 1 over negative 0.001 is negative 1,000. And I see a pattern here. The closer and closer I get to 2 from the left-hand side, it seems as though the values of y are getting smaller and smaller, faster and faster. Well, I plugged in 1.9, which is really close, and I got negative 10. So I'm assuming that as I approach 2 from the left-hand side, the values of y are just going to decrease. So I have a function that's decreasing, and I can say that the limit as x approaches c from the left-hand side of f of x, because the y values are getting smaller and smaller and smaller, I can say that limit is going towards negative infinity. I also want to do this and approach from the right-hand side. So let's go ahead and plug in numbers on the right-hand side of 2 and get progressively closer to 2. So on the right-hand side, I'm plugging in numbers like maybe 2.1. 2.1 is bigger than 2, but very close to it. 2.1 minus 2, well, that's 0.1, positive 0.1, and 1 over positive 0.1 is 10. And if I plug in 2.01, 2.01 is still a little closer to 2 than 2.1, but still on the right side. And if I plug that in, I'm going to get 100. And if you continue this pattern, 2.001, even closer to 2, you're going to get 1,000. As you approach 2 from the right-hand side, it seems like the values of y are getting larger and larger and larger. We are approaching positive infinity here. That means that I can say that this limit, as x approaches c from the right-hand side, I can say that limit is equal to infinity.